Okay. Okay. Where is the whiteboard here? I thought whiteboard is here. Okay. Anyway, we'll go by this. Okay, this lab is consisting of 3 parts. Okay, so VLSI lab. Having the first part is part 1. It's related to combinational circuit modeling. Next, part number 2 related to modeling of sequential circuits. And part 3, we focus on final modeling of finite state machines. Modeling of finite state machines and some related project works, project work. And part number 4, spice modeling. Part number 5, layout design. So okay, so these are the 5 parts are there in our lab. Okay, throughout this semester we have to follow this one. Okay, so in this one we have started off modeling of the combinational circuits. Just for this one, we introduced some concepts like first of all Vivado tool demonstration that I have done. Tool demo, that means how to use the tool that I have designed there. I have introduced it there. And now various circuit modelings that we have to use. Various circuits need to be modeled. Okay, so here the major part is there in the combinational circuit where we have to introduce all the modeling styles related to the circuits. Okay, For the sake of simplicity, I'm going to write one bit full adder. Okay, one bit full adder. This is the first experiment. You have to write in your program also. This is the lab number two. Lab number two. Okay. So the lab number one is actually introduction to HDL programming as well as FPGA. This information that I have given through the oral presentation as well as YouTube link also. I have given my own YouTube link also. I have given there. Okay. Lab number two will be considered as circuit modeling using different modeling styles. Okay, so that's what's today's topic. We focus mainly on taking the example of full adder. Okay, and we would like to write the verilog program in all the modeling styles. So the first modeling style is data flow, sorry, gate level. The second modeling style is data flow. The third modeling style is truth table or behavioral modeling. The fourth one is structural model. So these are the things that we would like to see in the today's class. It's just bench as well. Okay, is it clear to all of you? Okay, somebody has done. Okay, a remote system is not working. So let me call to Suresh, and then I will make you. I will arrange you the remote desktop. Okay, please wait. Okay, so I have informed him. Okay, he will respond to that one. Okay. Okay, fine. Okay. Have you done this programming? I just wait. He has responded. Okay, he will do it. I have already informed, so don't worry about it. Meanwhile, I'll complete the theoretical part as soon as possible. Then you can go ahead with your programming. Okay. Yeah. So due to the COVID, duties are assigned in different persons, so there is a miscommunication. Fine, no problem. The part one. Modeling of combinational circuits. Within this one, first lab number one is related to modeling of ladder using different modeling styles. So this is exclusively introduced to how to write the same block by using the different logic styles. So therefore you will habituated to write the same concept in different modeling styles. Okay. It is not necessary that all the programs you need to write in the different modeling styles. We can use according to our convenience. So sometimes behavioral is very suitable, sometimes data flow is very suitable, sometimes structural modeling is very suitable. According to that one, we have to follow that one. It's not necessary that every modeling style we have to use it for that one. But it is good to know that how to write a program same logic style will be implemented. So same logic is implemented by using different modeling styles. Okay, I hope the concept is clear to all of you. Okay, so this is what the today's aim: modeling of ladder using different modeling styles. Okay, just wait. Okay, fine. So how the full address look like? Let me write. Okay, this is what the simple block diagram of a full adder. Okay, so quickly I will do it all these things because we don't want to waste our time. So this is called A, B, C. This is called sum. This is called CO or C out I'm writing. Okay, so first one is I would like to write gate level modeling. Gate level modeling. Okay, so what is the logic diagram that is required for it? Okay, if you want to write the gate level modeling, gate level circuit is required. Okay, so I would like to write a 3-input exclusive OR gate. Okay, this will produce the sum signal A, B, and C. Everybody should know about this circuit diagram. How did you know about this? So as soon as we know about this full adder, for example, as soon as we know about this full adder, we know about its functionality. What is its functionality? First of all, its functionality is defined by using the truth table A, B, C, S, N, C naught. So what are the things are there here for it? Okay, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Some 0, 1, 1, and this is 0. This is 1, 0, 0. This is 1. What about this? This is 0, 0, 0, 1. This is 0, 1, 1, 1. So this is what the functionality of the full adder. Everybody knows about it. Okay. So from this one, we should know that C out is nothing but A exclusive, B exclusive, C. Okay, and C naught is nothing but AB plus BC plus CA. Okay, this is what only I have mentioned there. According to this particular Boolean equations, I have designed my logical circuitry for this. Okay, it requires AB. This is called AB. Okay, this is called BC. This is called CA. This is called C. This is called A. Or I can try to take it from here itself also. This is C. Okay, this is what the inside of your block diagram. Okay, I have previously mentioned about it this way also. So this is called A, this is called B, this is called C. So based on this one, we can write a verilog program for it. Okay, so how do you write a verilog program? Okay, I think you know very well about it. Okay, so okay, I'm writing very quickly so that you're also able to write very quickly. FA underscore data flow. So consisting of A, B, C, some comma C naught. Okay, and the inputs are A comma B comma C, and output is S comma C naught. Okay, and we can write just gate level modeling. So better write this is called G1, G2, G3, G4, G5, something like this. Okay, what about G1 now? I'll write just directly XOR. Okay, this is the keyword. The name of the gate is G1. First, I need to write output first of all. S comma A comma B comma C. Right now, similarly, I'll write AND gate. How many AND gates are? 3 AND gates are there. So AND gate is G2, and it's okay. That's yeah, fine. What about this one? This is called. Let me try it. This is called T1. This is called T2. This is called T3. Okay, what its value? T1 comma A comma B. So this I need to write 3 times. So just copy and then paste. And then paste. So, and I should remove these gates. This is called 2, 3, and this is 4. This is called 2, 3. This is called C actually. This is called AC. Okay, why we need to do this one? This is called B comma C, A comma C. Finally, we need to write OR gate. This is called G5. Its contents are C naught, T1 comma T2 comma T3. Okay, finally we need to write AND module, but don't forget to write T1, T2, T3. These are all whiles. So it is also keyword while. This is called T1 comma T2 comma T3. Agreed. So this is how we need to write. Very simply, we can write a half full adder gate level modeling. Okay. Okay. So that means what I have to do is that if you want to write a gate level modeling, gate level circuit is required. There is no doubt at all. But sometimes the circuit complexities increases, very difficult to understand the gate level modeling of a particular circuit. Therefore, it is possible, verilog given the provision is that we can directly use these equations in your program. So that is called data flow modeling. So the second one is data flow modeling. Okay, data flow modeling. So what is there inside of this one? The same concept only. So those who have not able to understand previously my classes, please try to understand here itself. Okay, so we don't want to bother about what is the internal circuitry of this. Okay, never, we don't bother about it, what it is. So directly we have DC sum and carry. It is down by the equation S is equal to A XOR B XOR C. C naught is equal to AB plus BC plus CA. Okay, so the same modeling style that I can use it here itself, but I want to remove unnecessary part related to our modeling style. Okay, so here, okay, I'm sorry, the name I have given here is the data flow. It's a gate level modeling, right? This is a gate level. Gate level. It's data flow modeling. Now, what is the unnecessary part? Wire from wire onwards, it is all things are unnecessary for us. So it is designed. It is taken by the synthesis tool. So just I can write only two simple equations by using the assign keyword. Assign S is equal to A XOR. No, A XOR is not. We should not use. We have to use verilog operators. So this is a verilog operator XOR A XOR B XOR C, right? Okay, we have to use another assignment statement. Assign C naught is equal to A ended with B. Okay, A ended with B, odd with B ended with C, odd with C ended with A. Okay, better I have to take user defined words with black letters. Okay, that's it. Okay, we can do it here. Okay, that's it. So therefore, the complexity reduces far better when compared with the gate level modeling. But here also, if the number of inputs are increases, very big length equations are need to be right. So there may be a possibility of errors in your equation. There may be a possibility there. So another one is called behavioral modeling. So we have to write a behavioral modeling. Okay. So the next one is called C is behavioral modeling. Behavioral modeling. What we try to do here is that, so instead of taking the Boolean equations, you can place the truth table directly. But in fact, actually, it's not the case of writing the Boolean equations. Sorry, the truth table, functional table, we have to write logic that we have to write. But for the first understanding, I would like to say that this is simply a truth table. Okay, you also keep it like that only. Later, for a specific truth table, we have to use user-defined primitive called a table, so that we have to follow that table later on. Okay, so this is what important for us now. Okay, so according to this one, we need to write. Here we have to write based on the always block. Here we have to write the equations. Here we have to describe the circuit based on always block. Okay, now how do I write like this? Better I have to take this program. Procedural statements I have to use. So where I need to write the procedural statement, I think you know very well about it. We have to write the procedural statement only at so we have to write the procedural statement only at always under the always block only. Okay, so unnecessary part we want to remove here. So what is the unnecessary part here now? So this assignment statement I don't want to use. Okay, instead I would like to use behavioral modeling. So if you want to use the behavioral modeling, first thing is that output must be a register data type. Reg yes comma C naught. Very, very important. Okay, so should not forget about this particular concept. Okay, that is important. Next, we need to write procedural statement. Procedural statement we have to write only in the always block. Always we have to write the output changes parameters. So what parameters will change the output? Those parameters we have to write. Those things we can call it as sensitivity list. So if A changes, B changes, C changes, obviously the output will changes, right? So this is very important. So between the begin and end, so begin and end, we need to write. So we need to write procedural statements. So one procedural statement I would like to hear is that what procedural statement is, let us write first of all. For simplicity, I would like to write if statement. Later we'll go for other things. So for a simple combinational circuit, something like this, it will be very difficult. It is sometimes very tedious job to write the behavioral modeling, but it's very advantageous as we have seen the counters, registers, some other complicated circuits. Behavioral modeling is very, very important and very simplest when compared to the other modeling styles, but very simple sometimes. A simple circuits we have to follow. Some tedious job is involved in this one as well. Okay, so yeah, if statement I'll write if. Okay, simply I'll write if A is equal to 0 and B equal to 0 and C equal to 0. If this is the case, okay, so what we observe that if this is the case, what is happening here? Some value is equal to 0, sum is equal to 0, and the C naught is also equal to 0. Just what we are doing here, we are not bothering about what is inside of the circuit. Whatever the truth table is there, that we are placing the truth table with the help of procedural statements. That's it. Okay, so please remember that point. So since actually these two things are there here, actually if that is true, this is happening. Okay, so but actually what we have to write here, two statements we have written. Actually this is what the meaning of the statement. So it is inside of this one, so that means below of that one. So that means the two statements are there. If this condition is true, these two statements must be executed. When we have two statements, it is better to write begin and end. It's very, very important. Okay, so if I write like this, it will take a lot of space. That's the reason why instead of writing this one, it is possible. Verilog has given a provision that after the semicolon, every statement is a separate statement. If the two separate statements are there, we can place it adjacent to each other. Okay, that is how we can write. So therefore, it is possible to write here, as well as it is possible to write below of that one also. I hope you understood the concept. Okay, so this type of statements I need to write 8 times. Okay, 8 times I need to write. Of course, so many methods are, so many ways also I can write it, but I'm telling you that very simplest and fundamental thing. First of all, I don't want to go for very complicated nature of writing this thing. So very simplest way also we can write it there, but I'm not interested to write right now. Okay, how many are there? 1, 2, 3, 4, 5. Another 3. Just I'm writing the truth table, nothing else in it. Okay. But provided that, see here. So very important thing is that we keep it here. Okay. See here. So the second statement will be executed only else if else the first statement is not true, then the second statement has to be executed. Okay, somewhat I need to modify this code, put it aside in this way. Yeah, just a second. Suresh. Okay, so student cheptanan. Can't okay. Oh, fine. Yeah, students, you are able to connect it to your to the college systems. Let's wait for some time. Then after this, you can go for it. Okay, so else if this is the statement, the first statement is false, then go to the second statement. Okay, if the second statement is false, then we have to go to the third statement. If the third statement is false, go to the fourth statement. If that is also false, then go to the fifth statement. If that is false, go to the sixth. If that is also false, go to the seventh. If that is also false, we have to go to eighth statement. Provided that each and every statement, we should remember that it's not 0, 0, it should be 1. I hope you understand. Okay, next is 0, 1, 0. I think I need to use another color. It is 1, it is 1. It is 1, 0, 0. This is 1, 0, 1. It is 1, 1, 0. It is 1, 1, 1. Whatever the sum and carry signals here now, it becomes 1. Okay, it is also 1. It is 0. It becomes 1. 0, 0. It becomes 1. What about here? 0, 0. Here it should be 1. Here it should be 0. Here it should be 1. Here it should be 1. Here it should be 1. I hope you understood the concept, right? So this is how we need to write a behavior model. As I mentioned that very clearly that since it is a simplest way that I have written, nothing we didn't bother about what is the crude logic behind this one. Simply the truth table I have fixed it there according to this one with the help of verilog constructs. Okay, so let us go quickly to the structural modeling as well. The structural modeling is actually when we have a circuit consisting of very big circuit having different sub blocks. Okay, sub blocks. So n number of sub blocks we have. So then structural modeling is a very structural modeling. We have structural modeling only we have to use. Is the first component, second, third, fourth, fifth, sixth. All these components we have to define. Later we have to connect it in your main program. Okay, so let us try to write a structural programming for this full adder. It is also similar to that of gate level modeling only. That means instead of the gates connection, we have to use component connections. But the component we have to define the previous, we have to define separately. So for example, here is the D is structural modeling. Structural modeling. Okay. So structural modeling is how do we look the full adder by using a component. For example, if I say that construct the full adder using half adders, using half adder. Okay, what is a half adder actually? What is a half adder? So something like this, I can write it. For example, if I considered a half adder here. Half adder we have defined very well, having two input signals. It produces the sum signal. It produces the carry signal. So we would like to take another half adder. Another half adder. It is called half adder. It is also called half adder. Okay, so it is called, for example, A, B. The output of this one, some output of this one is connected here, and externally we have to apply the carry in signal. It will produce the sum signal, right? So this part that you know very well from the basic understanding. See, okay, and this one, okay, and the carry of this one, both must be added together. It will produce Cout signal. So this is what the component declarations. This is the one component. This is another component. Okay, it is just like gate level modeling only, but half adder is not a gate circuit. It is beyond the gate level modeling. Okay, so therefore the sometimes some textbooks follow the structure modeling and gate level modeling. They will interchangeable with. Okay, but the structure modeling is specifically a component should be there. Gate level modeling is consisting of basic gates. So this is what the inside of your circuitry. Now we need to write the program for this. Okay. Okay. So what is required for us? We take a very simple modeling style. Gate level modeling I consider. Okay. So what is not required here? Okay. I want to remove all these things, not necessary, not required. Okay. So this is my, it is structural. So here also I would like to remove this name, data flow. It's a behavioral. So we can use any name, not a problem. Okay, so here what I can do is that I know very well that exclusive OR gate is, I have an OR gate is there. First I will write an OR gate. Okay, first I'll write an OR gate. Or what is the name of this gate? For example, G1, where it is available. So Cout is the output. And what is the input for this one? The names I didn't give. Okay, so let me give this is the name of this one is, for example, so C1, sorry, C2. This is called C1, for example. Okay, this is called C1 comma C2. Agreed? So immediately I'll write y is actually y C1 comma C2. Y C1 comma C2. Right? That is an OR gate I have written. So how I have written this OR gate, first output followed by the inputs, how I have written here. That is because the OR gate is definition is there in the Xilinx software. Okay, this definition is already available. Okay, but the half adder definition, the tool doesn't know about it. Okay, so therefore it is our own circuitry. Okay, so therefore we have to define that one. So before defining that one, first of all, that is also considered as one component. Let me call this is half adder. I don't want to write it as a keyboard. It is user defined, right? Half adder H here I'm writing here. So the name of this module is M1, for example. So it is available from where to where. What are the components are there? For example, first I want to write it is input A. I'll write another input is B. Next, this is called S1. Let me write S1 here because nothing else there, right? S1 here and C1 is here. So this is how I have written. That means I need to define what is this component is. So very, very important. I need to define what it is. Okay, later I will define what it is. Okay, similarly, I will write half adder. Another half adder is also there. Let me call this is M1. This is called M1 module 1. This is called module 2. This is called M2. So actually, what is the things are there? First S1 I am writing. S1 I'm writing, C1 I'm writing, S I'll write, and C2 I'll write. That's it. So this is how I have to write the top level module for the full adder using a structural modeling. What's very, very important thing is that I need to define what it is half adder is. How do I define a half adder? Okay, let me write a half adder here. Half adder. Same names that you can use or different names also we can use. No, not at all a problem. So let me write X here, Y here, sum here, carry here. Okay, this is an half adder. So how many ways that I can write a half adder again? Please remember, how many ways I can write a half adder? It is possible to write with the help of gate level modeling or data flow modeling or behavioral modeling also. In the three ways I can go for it. But it is not possible to write the half adder by using the structural modeling because it does not have any subcomponent. It doesn't require any kind of subcomponents. I hope you understand the point is. Okay. So therefore, the structural modeling for the half adder is not relevant. It is simply like a gate level modeling. Okay, but this very simplest method is that writing by using the data flow modeling. It's very easy. Equations are sufficient for that. Okay, so let us write a module name here. So let us write a module. What is the name that I should give? Anyone? Half adder name that I have to give. Right? I have to write half adder. HA. What other things are there here? First inputs I have written. Something like this input I have written. So X, comma Y, comma first, then some signal I have written. Then carry signal I have written. So actually we need to write this port assignment according to this one only we need to write here. According to this one only we need to write here. Okay, that means first of all half adder I need to declare first, then we have to write this one. Usually that is a procedure just only for the sake of your understanding I have written here, but actually this I need to write first. This I need to write first of all. Okay. So therefore accordingly we need to write half adder related input output according to the A and B and C. Agreed? Okay, fine. Next, out of all these things, inputs are X comma Y, X comma Y. Okay, next output is S comma C. Okay, now simple mathematical equation I can write, Boolean equation, sorry. Assign S is equal to A X or Y. Next, then another statement, assign C is equal to X ANDed with Y. It's very simple. Find the end module. Okay, so that's it. This is how we need to write. So this is what the structural modeling is all about. So is it clear to all of you, everyone from the class? So this is entirely verilog programming that we have to play with the entire course. Okay, either you can write it in the data flow gate level modeling or data flow or behavioral or maybe structural modeling. Okay, so this is the procedure. But you know that whatever the modeling style that you use, whether gate level modeling, data flow or behavioral modeling, the test bench is the same. Same test bench we have to follow. Okay, so for the data flow modeling, one particular test bench for behavioral is one type of behavioral test bench. It's not true. Okay, so the test bench means we have to apply A and B and C, and what is the A and B and C we need to describe. So that inputs only for all the modeling styles, right? So therefore we need not write separate modeling styles for test bench. So I'll also write the test bench quickly, and then you can practice it in your the lab. Okay, let us write the test bench. Test bench. So we have a test bench requires only the inputs. It should generate the input signals. So A should generate, B should generate, C should generate. Okay. Okay. So what is the A and B and C are must be written in the form of waveforms. Therefore, this is the one waveform. 1, 2, 3, 4, 1, 2, 3, and 4. This is, for example, A. And B is something like this. For two signals, it is low. Two signals, it is high. For two units, it is low. Another 2 units, it is high. For 1 unit, it is for C. This is called B. This is called C. C requires 1 unit high, 1 unit low. 1 unit high, 1 unit low. I hope you understand. This is the complete text vectors that we can apply for a full adder in order to test this one. And inside of this block, these are the waveforms are there in it. Okay, so let me write. This is, for example, 0, 5, 10, 20, 30. Sorry, Tarasana. Better uniformly we can consider. For example, 10, 20, 30, 40, 50, 60, 70. Okay, 70. At 80, we can stop this one. Okay, fine. Now we'll write a VLSI program for it to describe this waveforms with the help of module. The help of module. It's a test underscore ladder. Okay. All the inputs are declared as wire. All the inputs are declared as okay, fine. All the inputs are represented as a register data type. This is called A, comma, B, comma, C, and all the outputs are declared as a Y type. I hope you can see the screen quite clearly. Sum, comma, C out. Okay, and let us start with initial statement. Initial. Okay, let me call first of all what kind of circuit that we want to test. For example, I want to test gate level modeling. Then it's very important to note that this module name I have to call. So this is what I want to test. Okay, so this is important to fix it here. Okay, and so I have to give some space here. I want to write module name. It's a good practice to write a module name here. So whenever the synthesis tool will simulator will take very effectively if you write the module names, something like that. It's option actually. Okay. Okay, fine. Now initial. What we can write it here? Combination status right here. Begin. First of all, A is equal to 0, B is equal to 0, C is equal to 0. Okay, this is what we consider. A 0, B 0, C 0 at 0 time. At 10th nanoseconds of time, what about A? A is 0, B is 0, but C is 1. Okay, and exactly this point we are talking about. But that is valid up to the next 10 nanoseconds. Okay, that is valid up to this duration of the time. Starting from 10 nanoseconds, it is available up to the 20th nanoseconds. So what is this value? A equal to 0, B equal to 0, and C is equal to 1. Okay, so this must be, sorry, this must be repeated. Where it is, I didn't paste. Oh, somewhere it is copied. Okay, it's not copied, I think so. Copy and then paste it here. How many times I need to paste? 8 combinations are there, 8 times I need to copy. So simplest methods are also there. By using the for loop, I can do this one, but initial stages, we don't want to go for it because you will confuse all these things. First, to understand the fundamentals and apply the concepts. Okay, now I would like to change. This is the 1, this is 0, this is 1, both are 1. This is 1, that is 0. I'm sorry, this is 1 only. Okay, next, this is the 1, this is the 1, 1, 1, 0. This is 1, this is 1, both are 1. Finally, I need to write end. Okay, so I want to stop my simulation at some point. If I want to use a system task, I need to write initial. I want to stop my simulation at 80 nanoseconds, for example. 80 nanoseconds, $stop. Finally, I need to write end module. Okay, so this is what the test bench that we have to write. If you're using the data flow modeling, you change this one by using that particular module name. If you're using the behavioral modeling related block name that we have to use. Okay, so this is the entire verilog programming styles that we normally follow in the entire course. Okay, this is very, very important for you to understand. Okay, the same notations we have to use entire course. Okay, you please try to use these codes. Okay, I will post it in your WhatsApp group. So use this verilog code and try to execute this program in your system in Vivado tool. If you find the difficulty, I will here to explain you what is the problem with that. Okay. Okay, so I will try to rearrange this information more systematic way so that you people will understand. Okay. Okay. Okay, please try to connect this with systems. Meanwhile, you please try to connect to the college systems. So it is not possible to get the A4 size sheet. That's the reason why we have to somehow modify this one. Sir, can you please send me your some text message to my WhatsApp so that I will send this information to you, so that the students will make use of this code when it is necessary. Okay, please try to write on your own way. If you find problem, you see this one. Still, if you problem, please let me know. I will explain that concept. Okay. Okay, good. Okay, I will print this. CR, can you please send me your WhatsApp number?
Yes, sir. I'll text you, sir.
Text me.